Oh, no, wait, I was gonna say, I got that all crashing that piece of those. Maybe this.
Okay, so on the right is actually the thing from Windows today, and then on the left is actually the equations that I summarized for chapter 10. That's all the equations actually memorized for chapter 10. So you have some time, overlap of the equation for yourself.
No.
Oh, yeah. It's like it's strange. It's like I like to get the action. Bro, that's
Yeah. I can't, oh, I think like on the train and stuff. Yeah, can't feel on the train. I love some people.
yeah.
But and then that's the first meeting. I'm like, I said I would be in the hospital. I was just like, next. Or I could do it. Oh, because I was following things. Yes, also be able to- Yeah, yeah.
Yeah, he was down.
Subscribe.
So he didn't. It's the way it went. Really happy, yeah.
Yeah. Wonderful.
Yeah. He's working on it. No, it's just second year, second year. Yeah, they need someone. It's not like- yeah, it's just- You know, the 18th. That's all. He knows, he's too good at job. It's like a basic reading. I was very I know about facing. Never gonna do. But I honestly
Okay, let's get started. Okay, so any first welcome back. Okay, I hope you enjoy your break. Okay, any questions before we get started? So in the past couple of days, I think I answered many questions. Okay, I think all the questions I received, I've answered. If you ask a question, they haven't done my response. Somehow I miss it. Okay, so you can either come to me after the lecture, or you can just email me again. Okay, but I assume that I answer everybody's question. Okay. The other thing I noticed that students start to use the Q&A sections on our Teams, right? So I think that's actually a very efficient way to get an answer from me or from your friends in the class. Okay, so if you have more questions, feel free to post it over there. And I'll try to actually answer those as soon as possible. Okay. If you want to actually make sure I will actually know you post a question, you can tag me, right? You can add Tai-Yen and you will show up, you will pop up on my phone. And I know I can actually address those questions as soon as possible. All right. Okay, any other questions? No? Okay, so what we're going to do today is actually very simple. We are going to finish in chapter 10 and enter in chapter 11. Okay, so on the rule, I summarized the things we went through from the previous two lectures. All the things I wrote over there, there's nothing new. But those are things that you will need to memorize it. Okay. So in the past 2 days, I received a few emails saying that students start to feel some of the grading criteria doesn't make too much sense. For example, the student entered like 85% instead of 85 in the answer and was counted wrong. And the other one is actually the input the significant figures incorrectly and did not get the credit at all, right? Or when you use this some number of times 10 to the x power, you should actually input as exponential to the x power. And you did not actually follow the format and it was counted wrong. Okay, so I have nothing to do with that. That's actually the chemistry design. Okay, so when you enter in CHEM1312, you are going to do a lot of calculations, meaning like you actually write down your answer in a specific way so that the computer will actually recognize it. Okay, and the way that actually to write it is actually the way the field want to use. Okay, so even though it's actually the same answer, but if you input in different format, you are not going to get the points. Okay, of course, that's it's that's what it is. Okay, so I think it's also an opportunity for us to learn how to write things scientifically. I think that's good for you too. So instead of come to me and argue about that, maybe it's actually smarter to learn how to write the answer in the correct format, because you only do you good in the long run. Okay, so one thing I always tell my students is that if you spend all time arguing, you are not actually improving. Okay, so some of the rules, just follow it. Okay, if you know it's actually good rules, it's actually things that's going to be good for you, do it. Okay, complain just wasting your time, and you know you're actually so busy now. Okay, so we are just entering the second week of this semester, right? You can look back. The attendance will drop to about a third. Week 1. Okay, we just entered the second week. These things will actually get even worse when you enter the third, fourth week. Okay, and this is actually what happened. Okay, so I emphasize a lot to my students. I'm actually a graduate student and undergraduate student. Right? I tell them that, guys, you come to here because you want to. You want to get your degree. You want to have a better life. Then do it properly. Okay, don't waste your time. Don't waste your resource. Okay, so like I say in the first lecture, my job is to teach you how to play with one. Okay, and Gen Chem is just a subject that I use to hope you can see the things I care the most, right? Play for yourself. That's very important. All right. So get back to the content. Okay, so we go through a few concentration terms, go through a lot of definitions in last week. Okay, so today we're going to use all this knowledge. Okay, one of the big things for chapter 10, which we are going to do the homework this week, right, is concentration conversion. You are going to use the same concept over and over again this week. Okay, you have everything you need for today, for this week's homework. So go ahead and do it as early as possible. Okay. So the first big topic is the concentration conversion. Okay, so we need to actually memorize these terms. Then we need to actually understand the enthalpy change or the heat change when actually form a solution, right? Delta H solution. Okay, positive, negative mean different things. Okay, and then the other thing is actually if I give you a couple of compounds, can you predict they are going to dissolve with each other or not? Okay, so the basic principle is like dissolve the light. You need to have the ability to differentiate the molecule you're seeing is actually hydrophilic or hydrophobic, right? And it's actually very simple. If you look at the formula, if it contains OH, NH, yeah, consider it as hydrophilic. It only contains carbon, hydrogen, halides, consider it as hydrophobic. Okay, you need to know the effect of temperature and pressure on the solubility. Right? So these things you probably can comprehend through your daily life experience. Right. When you increase the temperature, the solid solute will dissolve more. Okay, and the gas will actually evaporate out. Okay. If you apply a high pressure to a solution, then the gas will be pushed into the water. Therefore, the solubility of the gas will increase. And this relationship can be described by the Henry's law. Equation-wise, it's very simple. C equals to the Henry's law constant Kh times the vapor pressure of pure solvent. Okay. Then we come to the very last one, the collective properties. Okay. This property will change when you increase the concentration of your solute particle. In fact, you have a good differentiation what is solute, what is solute particle. Okay. And you have a good understanding what is Bank-Hall coefficient I. Okay. But the basic idea is that the vapor pressure Vp and the freezing point is going to decrease when you increase the solute particle concentration. On the other hand, the boiling point and the osmotic pressure is going to increase. And the amount of increase or decrease, okay, there are 4 equations. For the vapor pressure calculation, you use rough law. Okay. For the change of freezing point, use delta Tf equals to I times K times N. Okay. Very similarly, delta Tb. These two actually look very similar. The only thing different is actually the constant you use is different. Okay, but all things will be specified inside your question. The very last one is actually your osmotic pressure pi equal to I times M times R times T. Okay. And then the R need to use 0.082 liter ATM per mole per K. Okay, and that's all. That's all the things we need to know for chapter 10. Okay, so nothing fancy. Okay, so we're going to go through a few examples so you can actually use these rules more frequently. Okay. If we still have time, then we actually enter chapter 11. Then we're going to talk about red laws. Okay, so the red law describes how fast the reaction can happen. There are actually 3 main topics in chapter 11 and only 3. First one is actually to know how to write the differential red law. Okay, basically, differential red law is actually what you can actually observe experimentally, and you how to actually write down the result in a scientific notation. That's what the differential red law is. Integrated red law is actually want to know how the concentration of your reactant evolve as a function of time. Okay. And then after we understand how to do those things, then we can understand how scientists actually define the reaction mechanism of the red law. And the very last one is actually a very famous equation, okay, activation energy. And we all know if you actually process at high activation energy, the process will be very slow. Okay, so how do we describe those processes in quantitative way? It's actually a very tough, very long topic for chapter 11. Okay, so I went through all these things very quickly. Okay, but that's pretty much all we learn for chapter 10 and chapter 11. All right? Everybody ready? Okay, so before we actually jump into the topic, let's use our beautiful point solution. Okay, first thing first. It's multiple choice. You can choose more than one. Okay. Okay, good. So the answer, okay, the question is asking which are the terms that doesn't belong to the concentration terms, right? So density and moles are the two that doesn't belong. So I think most of you actually answered this correctly. That's actually wonderful. Okay. Now we want to actually go to a more quantitative questions. So I list a couple of equations here. Okay. So what are those things? And to match the equation with the name. Okay, so I think there's actually more than 100 student answered things. Okay. The first term, mass of your solute divided by the formula with that's the definition of moles, right? Therefore, you know the answer has to be B, C, or D. Okay. The second term, mole of your solute divided by the mass of your solvent. Molality, right? That means actually the answer will be B already, right? So it's actually very straightforward. The third one, mass of solute divided by the sum of mass of solute and solvent times 100%. That's the mass percent, right? The fourth one, mole of your solute divided by the sum of mole of solute and mole of your solvent. That's your mole fraction. The next one, number 5, mole of solute divided by the volume of your solute and the molarity. Okay. And the very last one is the molarity, which is actually molarity times number of equivalent. Okay, so those are the 5 concentration terms we're going to use a lot today. You need to know the definition. Okay. Next one. It's multiple choice. Okay, there's actually more than one answer. Okay, so this question asks for substance that can dissolve in water, right? Therefore, if you're looking for the substance, they are hydrophilic, right? And in the note I provide in the very beginning of the class, I say, if you are a hydrophilic molecule, you typically contains OH, NH. Okay. The other things that I cannot say explicitly, but you should know is that if you are a salt, it will dissolve in water as well. Okay. So for the salt, the answer E and F, they are all salt. Okay. Everybody know how to differentiate you have a soluble salt. How to make a judgment. Okay. NaCl is actually easy case, right? Because you see the Na is in the 1A group. CO is in the 7A group. Everybody knows the difference between when I say 1A and 7A. 1A means actually they are the atoms who want to become positive one charge. Okay, so 1A, 2A group. Want to make sure everybody can follow this. So if you see an element belongs to 1A, 2A, okay, those are the atoms like to be positively charged. Okay, and they like to actually work with the 7A atoms. Those are the atoms like to be negatively charged. If you see those things combined, very likely there will be a salt. Okay, so every time you see sodium chloride, lithium chloride, potassium chloride, magnesium chloride, calcium chloride, those are salts. They are hydrophilic. They will dissolve in water. Okay, so the only thing that doesn't belong to 1A and 2A group, but still can be a very well-known soluble salt, is this. Okay, ammonium chloride. Okay, let's memorize it. One of the spiritual molecules they can memorize it. If you see the NH4 plus, CO minus, they are soluble in water. Okay? So those are the salts. But what if you don't have salts? Then you need to actually looking for the molecules that contain OH or NH, right? So it's a very simple concept. You look at the option A to B. You look at A, we only have C, H. That's all right. Nothing else. So it's hydrophobic. Okay. Second one, Br2 is hydrophobic. So those are the two answers you cannot choose. Okay. Third one, I guess it's a little bit more challenging. Okay. Fourth one, CH3, CH2, OH. Okay. So it is actually, there are actually two components. One is actually OH, right? That is actually part is going to make it hydrophilic. But you have CH3, CH2. If you have actually a very short CH, we call it CH chain. Okay, very short one, then the OH will dominate. It will become hydrophilic. However, if let's CH become very long, let's say longer than 6 carbon, okay, then that part will dominate. Okay, then molecule, even though you have OH, it will become hydrophobic. So when you're looking for those molecules, be careful. Okay, so you see a short carbon chains with OH, then safely you can say it's hydrophilic. Okay, so D is definitely one answer for this question. Okay, how about C? Anyone of you is actually biology major? There must be some. Okay, what's the molecule over there? C6H12O6. Sugar, glucose. Okay, so we all know glucose dissolves in water, right? Why? Because if we look into its chemical structures, there's actually a lot of OH within that 6 carbon chain. Okay, there's actually multiple OH. Okay, so let's actually count the things that it's difficult to teach because if you don't know the structure, it's just you won't be able to actually tell. Okay, but the rule of thumb is actually you see tons of oxygen here. I would guess is that hydrophilic, then hydrophobic. Okay, so the answer to this question will be C, D, E, F. Okay, I hope you actually get a good sense about how we did here. All right, so let's count up the warm-up sections for chapter 10. Okay, now we are going to finish all the questions that we have an answer for chapter 10. Okay, so any questions? short chain, I would say if you have less than 6 carbon, I would consider it as short. Of course, this is actually my personal summary, right? That's how I see examples, then I conclude that it's a good number to use. Okay, if there's no more question, let's go back to the questions. Okay, question number 2. What is the molality of an aqueous solution containing FeCl3 molecular weight 162.2 gram per mole with a mole fraction of FeCl3 of 0.15? Okay, so every time, okay, first thing first, what are the keywords? And? Very good. So when you see 2 concentration terms within a question, 99.99%, it will be a concentration conversion problems, right? Okay, so once you know what you're going to have, then do your QE path. How many of you actually understand what QE path is? Everybody heard this term, QE path? No? I actually learned from my son and my daughter, who is actually in elementary school. And I found it's actually a very powerful logical flow for solving the problem. Okay, Q stands for question. D stands for data. P stands for length. Okay, A stands for answer. C stands for check. Okay, so I don't think there's actually a way you can check whether your answer is correct or not. Okay, but you can still do the same logic. Okay, so Q, what are the things you are trying to solve? Molality, right? So every time you write down the molality, write down its equation as well. Okay, we know the molality is M equals to moles of your solute divided by mass of your solvent in kilogram, right? So this tells you, if you know the mole of your solute, if you know the mass of your solvent, then you're done. Okay? D, what's the data that you have? You have a mole fraction equals to 0.15, right? And then you have the formula weight is 162.2 gram per mole. Okay, anything else? That's it, right? So, and every time when you do this concentration conversion problem, you always need to make assumption. Okay, so what's the assumption to make? You need to just starting from your known concentration. Assume its denominator equals to 1. Okay, so in this case, what is actually a known concentration? It's your mole fractions, right? So mole fraction was defined as mole of your solute divided by the mole sum of your solute and solvent. Right, that's the definition of your mole fraction. Okay. So you need to assume the mole of your solute plus the mole of your solvent equals to 1. That's the assumption that you need to make so I can do this concentration conversion. And this pattern will always hold no matter what kind of concentration conversion you are going to do. Okay? So once you do this, okay, then you know, because your mole fraction of your solute is 0.15, right? Therefore, you know, the mole of your solute is going to equal to 0.15. The mole of your solvent is going to equal to 1 minus 0.15 equals to 0.85 mole. Okay? So now you know these things. It's cool. But this is actually eventually the things you want to solve, right? So the information you want to get is actually the mole of your solute, mass of your solvent. Okay, those are the two you need to actually solve. Do you get the mole of your solute now? Do you get this yet? We got this, right? Because that's what we have here. Do we get mass of my solvent? This guy, apparently you don't have it yet. That is the thing to go after. Okay, so how do you go after? Because right now you know the mole of your solvent is 0.85, right? So what's your solvent? Water, right? Because it's an aqueous solution, right? So you know your solvent is actually H2O. What's the molecular weight or formula weight of your H2O? Okay, let's just make it simple. 18 grams per mole. Right. The things you need is actually the mass of your solvent. Okay. Now you need to actually recall that the mole of my solvent will equal to the mass of my solvent divided by the formula weight. Right. Again, we come back to the very simple definition. And apparently, this is actually the things you want to calculate. Right. So you can actually rearrange this equation so that you know the mass of my solvent is going to equal to mole of my solvent times its formula weight. Right. What's the mole of your solvent? You got it here, right? So it's actually 0.85. Formula weight of your solvent, which is your water, is 18. Therefore, you know the mass of your solvent will equals to 15.3 gram. Right? But you are not just want to have the unit of gram, you want to have a unit of kilogram, right? So you have to convert this one into kilogram, which is divided by 1,000, right? Which will make it 0.0153 gram. Okay. So once you did have this, then you know your molarity will equals to, on the top is 0.15, at the bottom will be 0.0153. Okay, and then if you do like calculation, you're going to get a value of 9.8 molarity. Okay, and that will be your answer. So any questions so far? I want to emphasize the logic here. Okay, first thing first, every time you read a question, find the keyword. And the things you can find from this question is actually you see the two concentration curve. Therefore you know it's actually a concentration conversion formula. Right? Then you write out your QD path. Okay, write out it's actually a question you are trying to solve. Then you know it has to be molarity. Then write down the definition of molarity. So you know what are the quantity you need to calculate. Okay. And then write down your data, right? And also write down its definition. After that, you actually make the proper assumption. Then in this, I will answer your question. Then after that, you actually make the proper assumption. The assumption is always to make your denominators equals to 1. Okay. Then starting from there, then you'll start to see the terms that you need. Okay. And typically just follow the leads. Then you'll be able to solve all unknowns and eventually get to your answer. Okay, so that will be the pattern we're going to use. Okay. I also want to emphasize that all the things we say, all the questions we do, all the things I provide, they are available on Teams. Okay, everything you see here was recorded, and it will be uploaded to YouTube as well. Okay, so make sure you actually use those resources to help yourself. Okay, how do you know this is actually the solver is actually H2O? So let's look at this question again. That's actually another keyword I probably need to highlight, right? So if you see this keyword aqueous, okay, or sometimes they are going to make it even more subtle. They'll write something like this. Okay, so what we see within that little parenthesis, okay, if you see this AQ, it stands for aqueous. Okay. And then if you see aqueous, that means actually your solvent is water. Okay, but default of CHEM1312, the solvent is actually water. Yeah, so even you don't see anything, you feel like, I don't really know, I just want to guess. That's fine too. Guess it right now. Okay. And water is actually your best friend for CHEM1312. Okay. Any other questions? If not, let's do another one so that you get yourself familiar with this. Okay. So previously, we do actually a very similar thing for question number 1. Okay, we're still using the same logic, right? QD pack is still the same. But some of the some of the students actually come to me after the lecture and say, okay, how come we didn't actually use this information, the density information? Okay, and the answer to let's do that question is that because you don't need to, then why is it over there? Because the evil chemistry department want to confuse you. That's the only reason. Okay, but when should you use it? That's an even more important question, right? When you will need to use that density information. You will only use that when one of the concentration is molarity. Okay, we're going to show you one example of that. Okay, so question number 4. Okay, so the question says a 5 mass percent aqueous solution of nitric acid has a density of 1.05 gram per ml. Calculate the molarity of the solution. Okay. I don't know when you actually download the Hangout. If you download it actually very early, it may actually show molarity over there. Okay. But if that's the case, that's correct way. You can use this example to show you when you will need to use the density information. Okay, first thing first, what are the keywords? Okay, aqueous is a keyword. Molarity is a keyword. Let's actually another one. What's the other concentration term? So you know it's a concentration mass percent, right? So you know it's a concentration conversion part. Okay. Q. What's the things you're looking for? Molarity, right? Write down its definition. Moles of your solute divided by the volume of your solution in liters. Right, that's your Q. Data. 5 mass percent. Okay, let's do this then. What's your solvent? Aqueous, right? Therefore, your solvent will be H2O, right? What's your solute? HNO3. Okay. So with this being said, then you need to know your mass percent, right? So mass percent was defined as mass of your solute divided by mass of your solvent plus mass of your solute times 100%, right? So that's the definition of your mass percent. Okay, so it's all the data you have. Now you want to go from the known concentration to the unknown. Okay, you need to actually make assumption. So the assumption you're going to make is actually make your denominator equals to 1, right? And because there's actually 100%, there's actually 100 here. So you need to actually make sure the MB plus your MU equals to 100. So it will cancel out with this guy to make a 1. Okay, so this is actually only case you need to actually make your MU plus MB equals to 100. Okay, because it's actually a percentage. So make it 100. Okay, so once you make it 100, then 5% will tell you the mass of your solute equals to 5 grams. The mass of your solvent will equals to 100 minus 5 equals to 95 grams. Okay. So once you go to this point, right, and you check the things you need is what? The mole of your solute divided by yet. What you get is actually the mass of your solute, right? Which means you can calculate the mole of your solute by doing this. The mass of a solute is actually 5. What's the formula weight of your HNO3? Okay, you need to actually calculate it from the formula, right? So the formula weight of your HNO3 is equals to 63.01 gram per mole. Okay, so the way you calculate this number, again, you need to actually go to your periodic table. Okay, so I just want to give you I just want to make sure everybody know how to do it. Okay, so then you need to know what's the atomic weight of your H. 1.00 N here, right? 14.00 plus 3 oxygen, right? So 3 times oxygen, 15.999. Okay, so when you do this calculation, you can get the correct molecular weight of HNO3, which is going to equal to 63.01 gram per mole. Okay, so depending on your equation, you need to know how to use your periodic table to get the formula weight. Okay, get back to here. 63.01. Therefore, you can get the mole of your solute will be 0.0793 mole. Okay, the next thing is actually you want to know the volume of your solution, right? Here, this is actually the time that you need to use the density equation. Okay, density equals to mass over volume, right? You want to know the volume, then you can actually rewrite this as volume equals to mass divided by the density. So what's the mass of your solution? 100, right? Because mass of the solution equal to mass of your solute plus mass of your solvent. In this case is 100 grams, right? Density provided here is 1.05 gram per mole, right? Therefore, you need to divide by 1.05 gram per mole. Okay. So once you do that, you're going to get a volume of 95.2 ml. And they want to convert it to liters, which divide by 1,000. Therefore, you get 0.0952 liters. Okay, so that will be the volume of your solution. Okay, now you got the mole of your solute, the volume of your solution. Therefore, you know the molarity will simply equal to 0.0793 over 0.0952, which is going to give you a value of 0.83 molarity. Okay. So let's refresh the yes. How do I know what? Because we assume the mass of your solvent plus the mass of the solute equal to 100. Let's get back to here. So here we actually assume that the mass of your solute plus of mass of your solvent equal to 100 to start with. Right, and the mass of your solute plus the mass of the solvent is actually mass of your solution. Do you understand that? Yeah, so let's actually we will get 100. Okay. All right, so concept-wise, it's actually again, it's actually the same. Okay, so you start from a one known concentration. You need to make a proper assumption. Then go to the unknown concentration. All right, so this is actually only time you're going to use the density information. If you don't see molarity inside your question, then the density information just to confuse you. Okay. All right, so let's actually go question number 4. Okay, question number 5. How many moles of solute particles are presented in 50 ml of 3N-Na3PO4? Okay, how many moles of solute particles are presented in a given solution with no concentration? Okay. What's the Q? Moles of okay, so solute particle is actually a keyword that you need to be very careful. Solute particle is not the same as solute. Every time you see a solute particle, be alert. This is actually a time they want to test you. Do you have the concept of Bancroft coefficients? Okay. For example, okay. if you throw in the sodium chloride into water, then you have the sodium chloride aqueous solutions, right? So in this equation I just wrote, the solute is what? Is NaCl. This is your solute. This is the solute particle. There are two different things. You have a clear distinction between the two. Otherwise, you actually answer the wrong. You're going to provide the wrong answer to the question. Okay. So in this question, let's look at the data that you have, right? You have 50 mil 3N Na3PO4. Okay. So Na3PO4, this is actually your solute. It is not your solute particle. So it's not actually how many moles of Na3PO4 you have. Okay. So again, sodium, everybody's friend. Sodium always wants to exist as the sodium plus. Okay, therefore, when this guy dissolves inside water, you're going to have 3 sodium plus particle plus PO4, 3 minus. So this is called the multi-atom anions. Okay, they are very, very stable. Okay, they always form their own species. Okay, so PO4, okay, in this case, will actually become PO4 3 minus. Okay, so the things you want to see that is, if you have one solute, you are going to produce 3 plus 1 in total 4 solute particles. Okay, therefore, if you know the mole of your solute multiplied by 4, then you get the mole of your solute particle. Okay, so that's the basic things, basic concept of this question. Okay, so how do we calculate the mole of a solute? The mole is going to equals to, so here you can see it says 50 mil, right? And then concentration is molarity, right? So you know the concentration equals to the mole of your solute divided by the volume of your solution. Therefore, you can rewrite this. The mole of your solute is going to equal to the concentration in molarity times V in liters. Okay, concentration is 3. Volume is 50 divided by 1,000. Therefore, you know the mole you're going to have is 0.15. So you have that much moles of solute. Okay. So the mole of your solute particle is going to equal to 0.15 multiplied by 4. They will give you a value of 0.6. Right. And this question specifically says you need to take the log with a base of 10. Okay. So log of 0.6 will give you a value of negative 0.22. And that will be your answer. Okay, so keyword of this specific question is that you need to have a clear distinction between solute and solute particle. And if you can see the things, then this question is very straightforward, very easy. Okay, any questions for this? Cool. Next question. Okay, we went through this, went through that. Question number 8. Okay, consider the solution 0.04 m urea, 0.04 m AgNO3, 0.04 m CaCO2. Which one has the highest osmotic pressure, highest vapor pressure, highest boiling point? Okay, what are keywords here? So, vapor pressure, boiling point, osmotic pressure. What do I highlight these things? Because only talk about these terms in what? Collective property. Okay, so all these things actually all tells you is testing you the concept of collective properties. Okay. And in the very beginning of these lectures, we say what? If your solute particle concentration increase, then you're going to have lower vapor pressure, freezing point, higher boiling point, and osmotic pressure. Those are the concepts that you can use. Okay, these are the things that I wrote in the very beginning of the lecture, and that's how I solve this problem. All right, so now you should also have some idea. Okay, for all these things, for all this calculation of all this pressure or boiling point, freezing point, there's actually one thing involved is that there's actually a Bangkok coefficient I shows up. Okay. To make sure you actually know exactly what I'm talking about. Okay. So if you have solute particles generated by this of your solute, right, then I will actually contribute to the change of your vapor pressure, change of the boiling point, freezing point, and osmotic pressure. Okay. So now, with that in mind, come back to here. You have urea. You have AgNO3. You have CaCl2. Each of them is actually have less specific concentration, right? But you know the concentration is actually not enough because it has to be a concentration times your I. Then they will tell you who has the highest solute particle. Okay? What's the I of your urea? What is the number? Let's start from some simple one. What's the I for your AgNO3? 2. Okay, because you know your AgNO3 will become Ag plus NO3 minus 1 plus 1 give you 2, right? How about your calcium chloride? 3, because CaCl2 become 1 Ca2 plus 2 Cl minus, and 1 plus 2 equal to 3. Okay, how about urea? So if you look at the formula, Okay, what do you have over there? Carbon, oxygen, hydrogen. Right? No metals. Those we call it as organic compound. Okay. What kind of species will give you I larger than 1? It has to be salt or strong acid or strong base. Okay. Any other things? The I is going to be equal to 1, meaning they did not dissociate. Okay, once they dissolve, they still stay the same. Okay. So with that being said, then you know the effective solute particle concentration will be 1 times 0.04 for your urea, 2 times 0.04 for your HgNO3, 3 times 0.04 for your CaCO2. Okay. So who has highest effective concentration? Calcium chloride. Okay. Then silver nitrate. Then urea. Okay. So that's the order. Okay. So with that in mind, then you know your CaCl2 is going to have the lowest vapor pressure, lowest freezing point, but highest boiling point, osmotic pressure. Okay, can you associate to this conclusion? Okay, I just write down this, right? The larger the solute particle concentration, you're going to have the lowest vapor pressure, lowest freezing point, highest boiling point, and osmotic pressure. Okay. So with that in mind, then it asks you who is going to have the highest osmotic pressure. Then you know it has to be calcium chloride. Okay. Who is going to have the highest boiling point? It has to be calcium chloride, right? Who should be actually the highest vapor pressure? Okay. So it is actually very simple if you actually can see and understand the concept we described for the collective property. Okay. I spent a lot of time trying to actually say the things that I just circled, because those are the things that you need to know. And these are the questions you're going to encounter. Okay, so you calculate the effective concentration of your solute particle, which will equal to the I times your concentration terms. Okay, so that's how you solve question number 8. How many questions we have? 10, right? Okay, 2 more, then that's it. Oh, no, 11. Okay, we'll see. Okay, number 9, calculate the boiling point in degrees C of a solution made by dissolving 3 grams of ethylene glycol in 10 grams of water. The kBp of the solvent is 0.512 K per molality, and the normal boiling point is 373 K. So what are the keywords? Boiling point. So every time you see these boiling points, freezing points, vapor pressure or osmotic pressure, that's the property, right? And then therefore you know the Q is actually to solve the T boiling point. Okay, data. You have 3 grams of ethylene glycol. Okay, so this is actually your solvent or solute. Solute. Okay, in 10 grams of water. So water is actually your solvent. Okay, and they tell you the KBP equals to 0.512 K per molarity. And then the normal boiling point is 373 K. So those are the data that you have. Okay. Then plane, because we know it is actually the collective property. Talking about the boiling point, the equation that we give you is delta TB equals to I times your KBP times your molarity. Right, this will tell you how much temperature change is going to cause when you throw in different amount of solute into the water. Okay, what's your I? What's your I? It's a salt. So every time when I say it's a salt, okay, you want to looking for what clue? Does it contain 1A or 2A metals? Ionic compounds. Those are the good clues you want to actually have. If it doesn't, then guess I equals to 1. Okay. But the bottom line is actually very simple. If you look at the formula, it actually gives you the formula, right? It's all carbon, oxygen, hydrogen, nitrogen. It's all organic compounds. Organic compounds, I equals to 1. Okay, therefore you know I equals to 1. KBP 0.512. Right? Times N. N is actually the molarity, which is the mole of your solute divided by the mass of your solvent in kilogram. Okay, so how do you calculate the mole of your solute? Will be the mass of your solute divided by the formula weight. The mass of the solute is actually 3 grams. Formula weight is, again, to calculate the formula weight. I will just give you the number here. $62.07. Okay. The mass of your solvent, you know, is actually 10 grams converted to kilogram, 0.01. Okay. Therefore, the molarity will equals to the mole of your solute divided by the mass of your solvent, which is going to give you a value of 4.83. Okay, so once you get this, go back to here, then you'll be 1 times 0.512 times 4.83. And once you do that calculation, you're going to get a value of 2.48 K. Okay. So up to this point, what you calculate will be the temperature change. Okay, the temperature change is actually 2.84 K. But this is actually not what the question is asking, right? It's asking what will be the final boiling point. Okay, so to calculate this, you need to do one more step, right? The final boiling point should be the initial normal boiling point plus the delta TB. So they will be 373 K plus 2.48 K. It will be 275.48 K. I need to convert it to degree C, right? So minus 273, there will be 102.48 degree C. So this will be your final answer. Okay. The things I want to emphasize is here. I put plus here, right? Because boiling point is going to elevate. You can have more solute. So it will be the original normal boiling point plus the temperature differences. Okay. But for the freezing point, it will be the opposite. Okay, because freezing point depression, okay, it will be the normal freezing point subtract the delta TDF. Okay, so I hope you can see that. Okay, so that's how you solve question number 9. I guess we can only finish 10 then. Okay, number 10 is actually very similar to question number 9. Okay, so let's look at the question. The 5 gram of unknown non-electrolyte dissolved in 50 gram of acetone. The boiling point increased by 2 degrees C. If the kBp of the solvent is 1.71 Kelvin per molarity, calculate the molar mass of the unknown solute. What's the keyword here? Okay, every time you see boiling point, freezing point, vapor pressure, osmotic pressure, collective property. Okay, so they have the associated equations, right? So boiling point. Okay, let's do the QD pack first. Okay, Q is actually want to know the molar mass, right? Formula weight of your solute, right? That's the things we want to solve. But the things you know is actually the delta TB equals to 2. And then, so the solute is a non-electrolyte. Your solvent is 50 gram acetone, right? Your kBp equals to 1.71 Kelvin per molarity. Right, that's all the data you have. Okay. So here you come to this point, right? So this is actually things you need to you need to actually get stuff from here. Delta TB is going to equals to I times kBp times molarity, right? Delta TB equals to 2. What's your I? 1, right? How do you know? It's a non-electrolyte, right? So every time you see this keyword, non-electrolyte, mathematically, what it trying to tell you is that I equals to 1. Okay? Do you know your kBp? You do, right? 1.71. Do you know your molarity? You don't. Okay, but you do know the molarity was defined as moles of your solute divided by the mass of your solvent in kilogram. Okay, you do know the mass of your solvent, right? Therefore, you know this one will equal to 50 divided by 1,000, right? How about mole of your solute? How many gram you have? 5 gram, right? Divided by the formula weight. That's the things we can write, right? So if you look at this, the only unknown is actually your formula weight. Therefore, by solving these equations, you will be able to know your formula weight is going to equal to 85.5 gram per mole. Okay, so let's actually how you solve this problem. Okay, so again, the first thing is actually identify keywords because you see these boiling points, you know it's a collective property, right? And then you know the equation that associated with boiling point is delta TB equals I times KBP times your N. Okay, then you check out what other things that you know. Then you realize the only unknown is actually the formula weight, which is actually the things that this question is asking for. Okay. Let me see. Okay, so question number 11 is basically the same. But these things in change is talking to what? Osmotic pressure. Okay, so I don't think I have enough time to finish this one. So go back home and do this. We'll actually finish this one in the next lecture and we'll end it here. Thank you.